In preparation for this semester's organic laboratories, I want to give a brief introduction to IR spectroscopy. IR is short for infrared, and spectroscopy implies viewing, that's scopy, using light spectroscopy in the infrared region, and we'll define that in just a moment. IR spectroscopy is a common method of analysis for organic compounds. In fact, virtually all organic molecules absorb IR, and IR is essentially heat. To the right here I have a photograph that I borrowed from Wikipedia. It shows an infrared image taken with infrared film. Notice that lighter areas in color represent higher temperatures and darker colors represent colder temperatures. Here's an infrared image of a human. Notice that the temperature varies with parts of the body. In this image, the higher temperatures are indicated by red and lower temperatures closer to the blue region of the spectrum. There are 7 types of electromagnetic radiation, EMR. Look at the scale below. At the left side we have high energy, high frequency, short wavelength, EMR like gamma rays and X-rays and UV rays. To the far right we have low energy, low frequency and long wavelength radiation, including TV and radio waves and microwaves. In the middle we have the visible spectrum, whose wavelength varies between 400 and 800 nanometers, or 0.4 to 0.8 microns approximately. And then just beyond the visible we have the infrared, 800 nanometers to a millimeter, or 0.8 microns to 1,000 microns. Pretty broad range, more than 1,000-fold increase. In fact, the word infra means beyond or below. So we can think of it as being beyond in terms of wavelength. So its wavelength is greater than that of red light, or its frequency is less than red light. Humans cannot see in the infrared region of the electromagnetic spectrum, but certain insects and animals, like mosquitoes and bats and snakes, can use portions of the infrared spectrum for vision. That is, they can see in the dark. So if you think you can escape a mosquito by hiding under the covers, you'll never escape. It can see your heat signature. Good to know, right? The IR spectrum is divided into 3 regions: the near IR, the mid IR, and the far IR. And as you can see, the near IR has a wavelength just slightly greater than the visible. The far IR has a wavelength that's considerably longer than the visible, just a little shorter than the microwave region, and the mid IR is, of course, in the middle range. The wavelength of the mid IR runs from 2.5 up to 25 microns. You also see another scale just below that. This is 4,000 centimeters to the minus 1 down to 400 centimeters to the minus 1. This unit is called a wave number. And wave number has a unit of centimeters to the minus 1, and the symbol looks like the letter V. This is the Greek letter N, which is pronounced nu. Nu with an overbar is wave number, and actually it's a unit of frequency, as I will show you on the next page. Let's learn how to convert between wavelength in microns and wave number in centimeters to the minus 1. So here's the conversion. Wave number is equal to 1 over wavelength in centimeters to the minus 1. We will be converting between microns and centimeters. So here are the metric multipliers that every student is expected to have memorized. On the scale we see centi and micro. They differ by a factor of 10 to the 4. We can say that 1 centimeter is 10 to the 4, or 10,000 microns. Or 10,000 microns is equal to 1 centimeter. It's easiest to avoid negative exponents and just use positive exponents, so we can say it takes many, that is 10 to the 4, of the small units, microns, to make 1 of the large unit, centimeters. Let's get some practice. Let's convert 2.5 microns wavelength two wave numbers. So we'll say the wave number corresponding to 2.5 microns is equal to 1 over the wavelength in centimeters, which is equal to 1 over 2.5 microns. And we'll convert that to centimeters. So there's 1 centimeter per 10 to the 4 microns. I can invert and multiply this fraction and write this as 10 to the 4 microns per centimeter divided by 2.5 microns. You can see the units of microns will cancel, and we'll have units of centimeters to the minus 1. So I'll write this as 10,000 microns per centimeter over 2.5 microns. So 2.5 goes into 10 4 times, into 100 40 times, into 1,000 400 times, and into 10,000 4,000 times. This is 4,000 centimeters to the minus 1 is equivalent to 2.5 microns. Let's try it at the other end of the IR spectrum. Let's calculate the wave number corresponding to 25 microns. Is 1 over the wavelength in centimeters equals 1 over 25 microns times, convert that to centimeters, invert the fraction, 10 to the 4 or 10,000 microns per centimeter divided by 25 microns. So 25 goes into 100 4 times, 1,000 40 times, and 10,000 400 times. That's 400 centimeters to the minus 1 corresponds to a wavelength of 25 microns. One more time. Let's pick 5 microns. The wave number is equal to 1 over 5 microns times 1 centimeter per 10 to the 4 microns, or 10,000 microns per centimeter divided by 5 microns. So 5 goes into 10 twice, 100 20 times, 1,000 200 times, and 10,000 2,000 times. Centimeters to the minus 1. So I want to make the case that wave number is actually a unit of frequency. You're probably familiar with this expression. The speed of light is a constant. It's equal to frequency times wavelength. Rearranging for frequency, we have frequency is a constant over wavelength, and compare the formula for wave number, it's 1 over the wavelength. So notice that the formula for wave number and frequency only differ by a constant factor, like speed of light. Since frequency and wave number are both inversely related to wavelength, wave number is also a unit of frequency. We need to digress for a moment to introduce you to some alkyl group names. We will restrict ourselves to hydrocarbons in this first lesson, and hydrocarbons are compounds made of only hydrogen and carbon. So alkanes are saturated hydrocarbons, that is, they have no pi bonds. For example, alkanes are saturated hydrocarbons, as opposed to alkenes, alkynes, and aromatics or arenes, which have 1 or more pi bonds in them. Now consider the alkane 2-methylbutane. Here it is, 1,2-methyl 4 carbons butane, 2-methylbutane in a UPAC, or isopentane, the common name. In either case, it's the same molecule, C5H12. Within isopentane, we have several alkyl groups. The CH3 something group, this here group, is referred to as a methyl group. The CH2, let's use a different color, the methyl group CH2 with 2 bonds, 2 single bonds. That is called a methylene group. And this carbon with 3 single bonds is referred to as a methyne group. In fact, many organic molecules can be named if we simply know the name of a few alkyl groups. For example, CH3Cl we now can recognize as being methyl chloride. And here CH3OH is methyl alcohol. CH3OCH3, it makes sense that it's called dimethyl ether. And CH2Cl2 is methylene chloride. Recall that CH2 is a methylene group. Most IR spectrometers are designed to work in the mid-IR range. Near IR and far IR spectrometers are less common. They do have important specific applications, but they're relatively narrow in their scope. The mid-IR spectrometer gives the most information about a broad range of organic molecules. And so that's what we're going to look at, is the mid-IR spectrometer. An IR spectrometer irradiates a sample with the entire mid-IR spectrum from 4,000 to 400 wave numbers. And almost all organic compounds absorb one or more frequencies in the mid-IR range. When an organic molecule absorbs infrared radiation, it causes its covalent bonds to vibrate. And there are actually 2 kinds of vibration. There's stretching and bending. Stretching vibrations involve bond length increase and decrease, whereas bending vibrations changes the bond angle. Take a look at some video clips from Wikipedia. So there are, in fact, 2 different kinds of stretching. On the left we see symmetric stretching. The yellow ball represents a carbon atom, and the blue balls represent hydrogen atoms, and the black lines represent the bond lengths. And you can see the bond lengths are increasing and decreasing. That is, they're stretching. They're stretching symmetrically, or they're stretching asymmetrically. Both types of stretching occur within a carbon to hydrogen bond. There are, in fact, 4 kinds of bending vibrations. You see on the left scissoring. Action is like a pair of scissors. Notice that the bonds are not stretching, but rather the angles are changing. They're bending. On the right-hand side we see what's called rocking. These are 2 types of bending vibrations. There are 2 more. 2 more bending vibrations you see on the left, wagging. Again, the bond angle is changing rather than the bond length. It's symmetric on the left, and twisting on the right is asymmetric, if you will. Here are all 6 kinds of vibration that can occur in a methylene group, CH2 group. A methylene group will actually absorb at 6 different wavelengths in the mid-IR, giving rise to 6 different types of vibration. 2 types of stretching, 4 types of bending. You can view these on Wikipedia. A given type of absorption, example symmetric methylene bend, can be seen at approximately the same wavelength, 1470 plus or minus 5 to 10 wave numbers in all organic compounds. So we can identify a methylene group in any organic molecule. Now, some IR absorptions are weak. Others overlap. They occur at the same wavelength or very close to the same wavelength. So not all are seen on a given IR spectrum, but most organic molecules contain several different alkyl groups, each absorbing at multiple wavelengths. And so the IR spectrum of organic molecules are usually complex, containing many absorption bands. The pi bonds of unsaturated hydrocarbons have their own unique set of absorptions, making their identification possible in organic molecules. Let's look at the infrared spectrum of a simple hydrocarbon, an unbranched straight chain alkane, hexane. It has 2 methyl groups on each end enclosing 4 methylene groups. Here's its spectrum. In an infrared spectrometer, an organic sample is placed between the IR source, here's the source, that would be a heat lamp basically, and a detector, here's our detector. The spectrometer emits infrared radiation of varying frequencies from 4,000 down to 400 wave numbers. That's on the x-axis. Now, it runs all those frequencies in a short space of time, 5 to 10 seconds. Usually the instrument collects that 4 times and then averages the results. The baseline up here represents high percent transmittance, and it represents frequencies at which little or no absorbance of the infrared beam is occurring. And so most of the emitted radiation strikes the detector. Our baseline is up here. At certain frequencies, various groups like methyls and methylene groups absorb infrared radiation and they vibrate. At these frequencies, less radiation strikes the detector and the percent transmittance drops. So we have absorption bands where parts of the molecule vibrate in response to the absorbed infrared radiation. We see the absorption bands at these frequencies, then we look at tables to determine which groups might be present to cause these absorptions. So let's look at a sample table. So the methylene groups, as we saw in the video clips, exhibit 6 types of vibrations, 2 stretches and 4 bends. The methyl groups, they exhibit their own absorptions, 4 types of vibrations, 2 stretches and 2 bends. Larger branched organic molecules exhibit more vibrations, and each vibration occurs at a different frequency, somewhere between 4,000 and 400 wave numbers. Now, the spectrometer cannot necessarily resolve all of them, so we see about 4 absorption bands. Furthermore, some of them are weak and difficult to interpret. We use some fairly specific notation. New AS stands for an asymmetric stretch. In this case of a methylene group, it occurs at about 29-25 wave numbers, right in here, and again at 28-50 wave numbers, and that's a symmetric stretch in this group here. The methylene group also absorbs. This is a symmetric bend. Delta is a symbol for bend, S for symmetric. It occurs at about 1470, right in here. And it also has a rocking vibration. It's a type of bend called a rock. The symbol is rho, Greek letter rho. Looks like the density symbol for methylene groups at 720 down here. Typically you need at least 4 or more in a row in order to be able to distinguish this peak, but it's quite sharp and it grows with the number of methylene groups in sequence. That's the methylene groups. For the methyl groups, we have asymmetric stretches at 2960, which overlap with the asymmetric stretches of the methylene groups. We also have a symmetric stretch for a methyl group at 2870 here, which overlaps with the symmetric stretch of the methylene groups at 2850 wave numbers. The methyl group also has an asymmetric bend at 1460, which happens to overlap the 1470 absorption of the symmetric bend of the methylene group. And then methyl groups also have a symmetric bend like an umbrella that opens and closes at 1380. So when I look at an IR spectrum, I can identify very quickly if a methyl group is present. There's a unique absorption at 1380 wave numbers. There are multiple weak carbon-to-carbon bands over a broad range from 1200 down to about 800 wave numbers in here. This is often referred to as the fingerprint region. Difficult for a human to discern it, but like a computer can read a barcode, a computer can read this fingerprint region and often get a fingerprint or exact match of an organic compound. So that's it for the introduction to IR. But each week, as you perform an experiment in the lab, you'll find there is a video clip explaining how to interpret the infrared scans of the compounds used in that week's lab. Thanks for watching.